Welcome back. So this is a new module and I'll start with convex optimization here. But before I get started, I just wanted to make a couple of notes. So I think really hard before I introduce something which is very dry or mathematical. But after thinking for a while, I thought that it's important to introduce optimization, at least some parts of it, before we get started with machine learning. And that will accelerate our learning in machine learning itself. So that's why I wanted to cover a bit of convex optimization. I understand that this module can be a bit dry and mechanical, but we need this so that we can learn ML in a quicker way. So it will feel like it's just a lot of definitions of mathematical entities, and that's partially true. But later on, you might realize that whatever you are seeing right now is everywhere. And obviously, optimization and ML is deeply connected, and it totally makes sense to get started with optimization. We won't go into too much of depth for this topic, but I just wanted to introduce a couple of things and then get started with ML. And as and when we need whatever algorithms for training our ML model, we'll cover it at that moment. And in a way, this just improves your maturity. It might feel useless till you see applications in ML. And trust me that this dry module will take you a long way. So with that, let's get started with convex optimization. So let's start with a very simple problem. Okay, so let's take this scenario. So we have apples and we have lemon, right? Now let's say apple costs you 50 rupees, which is my local currency. And let's say one lemon costs you 10 rupees in my local currency. Now, obviously, both of them have some level of vitamin C. So let's say apple has in a single serving, in one apple, there's 10 mg of vitamin C. And let's say for a lemon, we have like 31 mg. And then each of them also have calories, right? So let's say for apple, we have 116 calories, and for lemon we have 17 calories, right? So this one is the cost, this one is vitamin C, and this one is calorie, right? Okay, so now we have this situation that we know all this stuff about apple and lemon, and now what I want to try to do is try to figure out how much apple and how much lemon I should take every day to reach a certain budget. So let's say my goal is that I want to minimize the cost. So I want to minimize the cost of apple and lemons. That's the goal. And I have some constraints like total vitamin C from apple and lemon. So vitamin C from apple and lemon should be greater than equal to some budget for vitamin C. Similarly, I should like make a separator. And I also want something like the calorie from apple and lemon, how much I'm consuming, should also be greater than some budget, right, for calorie. So that's the main idea, that we are trying to solve an optimization problem where I'm trying to find out the number of apples and lemons I should consume so that my total vitamin C consumption is beyond a budget, and my total calorie consumption also is beyond a certain budget, right? So that's the idea. So let us write that formally. So what we are trying to do is we want to minimize the cost of apples and lemons, right? So let's assume that we are eating A apples and L lemons. These are counts. So what would be my total cost, right? My total cost would be the cost of apples into number of apples plus the cost of lemons into number of lemons, right? It makes sense, right? This is the total cost. And what I'm searching for is number of apples and number of lemons. So we are minimizing over A and L. That's my variables. These are called optimization variables. Okay. Now I also told you there were certain budgets, right? So let's first calculate the total consumption of vitamin if I eat A apples and L lemons. So let's do that. So that would be my vitamin C in apple times number of apples plus vitamin C in lemon times number of lemon. So this is my total vitamin C consumption, and that should be greater than equal to my vitamin C budget, right? This is my total vitamin C, right? Now there was also a calorie budget. So again, what I'll do is I'll have a thing like calorie for apple times number of apples plus calorie for lemon times number of lemon. So this becomes my total calorie from lemon and apple. This also had a budget that I should exceed a certain value. So let's say that is called calorie budget, right? So now we can see that we are trying to minimize the total cost of apple and lemon subject to two constraints. These two are called constraints. So what we are trying to do is we are trying to minimize the cost of what we are consuming. Subject to some constraints, the total vitamin C should exceed the vitamin budget, and total calorie should also exceed the calorie budget, right? So this is an example of optimization problem, okay? And also we know the values, right? We know the cost A, cost L here because we have seen cost is 50 rupees and 10 rupees for apple and lemons. And vitamin C in apple and lemon is also there, which is 10 mg and 31 mg. And then you can also see the calorie, right? Apple has 116 calories and lemon has 17 calories. So basically we know all these values, we just don't know A and L, right? So if I'm able to somehow solve for a value of A and L, there could be many possible values of A and L which satisfies these constraints. But I need to select those values which will give me the lowest total cost. That's the goal, right? So let's try to solve it. But before I do that, okay, for the moment, let's focus on the constraints. So what does a constraint look like, right? So let's start a new page. So the constraint looks like something like this, right? Like vitamin C in apple times A plus vitamin C in lemon times L is less than equal to some budget B, right? Now, this A and this L are the optimization variables. We don't know that, we have to find it. And these things are just some numbers, right? So we can just see it like A times A plus B times L is less than equal to some C, right? So there's some inequality. So let's first focus on equality. So it is just A times A plus B times L is equal to C. And if you try to plot it, what we can see is like, let's say my x-axis is lemons, number of lemons, y-axis is number of apples. And let's say if I'm plotting this line, and let's say this looks something like this, right? This is my AA plus BL is equals to C. And it can happen that this quantity less than equal to C might be one side of this line. So this whole area is my feasible space, right? So this is my feasible space for my vitamins, vitamin C. Now let's take another line for next budget. There was also a calorie budget, right? So let's say that would be D times A plus E times L is equals to F. So this is my new equation, right? And let's say that line looks something like this. So that line looks something like this. Let's say maybe like this. So this is another constraint. And what we need is that both these constraints should be satisfied simultaneously, right? So if I color it in a different color, let's say blue, then this is the area which is allowed, where both of them are satisfied. So obviously these areas are allowed, but you'll see that here I'm drawing this boundary, right? So this is what is allowed, and this part is not allowed. This is not allowed. So basically what is happening is we have two constraints in two different color. Both is a half space or something. So we'll look at all these things, but what I'm trying to say is that each of these constraints shades a region in this 2D, and only where these two areas intersect, which is this blue area which I've shaded this area, right? So this area which I've shaded, so my solution can only come from this area. For example, maybe this is a point here, which is a combination of x comma y, which is L comma A, right? So that's one possible solution. This is another possible solution, which is, let's say, L2, A2. So these are possible solutions, but there's also another side. So this one is not possible because it doesn't follow the constraint, right? So this is called infeasible. These two are called feasible solution, right? So basically, if I just look at the constraints, it will tell me that this is a region where solutions might lie. This is a region where solution cannot lie, right? And in the feasible space, we'll search for the solution. So that's the main idea. And then we have a cost on top of it, that from all these feasible possibilities, I have to find one which minimizes my cost. So that's the goal. Okay, so let's try to solve this problem using a library called cvxpy, and we'll see a couple of examples in this section. Okay, so this is my Visual Studio code, and you might have to install this. So you can simply use python -m pip install cvxpy, or additionally you could add these things in the brackets. Either way, whatever we are doing should work, and you can always go to this website and follow the installation instructions. Okay. So these were the details we had. Like the cost of lemon was 10 rupees, cost of an apple is 50 rupees, and assuming that 1 unit of lemon is like 60 grams almost, 1 unit of apple is like 220 gramish. So these are the reasonable sized apples and lemons, which has these costs. Then in vitamin C terms, these units will have 31 milligram and 10 milligram of vitamin C respectively. And then lemon has 17 calories and apple has 116 calories. And what we want to find is how many apples and how many oranges we want to do it. So we can clear all, we can run all, and it immediately completes. And we'll look at this code in a moment, but see what we have got, right? So if we eat like almost 6.5 apples and 2.75 lemons, then our cost will be 352 rupees. So basically what it's saying is that in 350 kind of rupees, I can get whatever calorie I want to consume, and that would be the minimum cost for that budget, for that vitamin and calorie budget. So that's the idea. So let's use cvxpy and get our solution. So first I import my cvxpy by using import cvxpy as cp. Then I initialize the things which I know. For example, the cost of an apple is 50 rupees, the cost of lemon is 10 rupees. So that's what we have done here. Then an apple has 10 milligram of vitamin C and lemon has 31. And then calorie from an apple is 116, lemon is 17. So all these we have encoded into variables. And then I've decided on some budget. For example, let's say I want my vitamin C budget at a daily level to be 150 mg. And my calorie budget from these two items, let's say, is 800 calories, right? So once I have these things, I can use the cvxpy library to build up an optimization problem and we'll try to solve it. So first what we do is we declare our variables, and these variables are scalars, right? These are counts. So our number of apples A is just cp dot variable. That's how I declare that this is an optimization variable. And the same thing for lemon. Next, what we have to do is create an objective function. And we had seen this objective function, right? Which is minimize the cost of apple and the cost of lemon, the total cost, the sum of those. So we'll define that. So our objective is equals to cp dot minimize because I want to minimize the cost. And then our cost is the total cost of apple will be cost of one apple into number of apples plus cost of one lemon into number of lemons, right? So this is my objective. This is called an objective. Then we declare constraints. What are the constraints? So the first constraint is vitamin C in apple times apple is basically the total vitamin C coming from an apple. The second term is basically vitamin C of a lemon into number of lemons. So total vitamin C coming from lemon. So total vitamin C in total will be the sum of these, which should be greater than some vitamin C budget. So that's my first constraint. The second constraint is calories coming from an apple, which is the first term. Calories coming from the lemon, which is the second term. And the total calorie will be just the sum of these two terms, which should be greater than some calorie budget. So that's my second constraint. Now the thing about mathematical optimization is it's very precise. And we cannot consume negative apples and negative lemons. We cannot get out an apple from us, from our body, right? So we have to put in constraints that at least we have to consume either no apple, which is equal to 0, or some positive quantity of apples. Similarly, for lemons, we have to consume at least 0 or more lemons. So that's the total constraints. Now we'll create a problem, which is just objective and constraints. So we'll see later that this form of problem is called a linear program because everything is a linear thing, right? Cost is linear, constraint is linear. So that's why it's called a linear program, and we'll revisit it. Don't worry about it, but just see how simple it is to form an optimization problem intuitively, right? I've explained it to you in English, right? You don't need to know all the fancy terms like linear program and all, but at least this makes sense, right? I have to minimize the total cost which I'm spending. I want to like fulfill my vitamin budget and calorie budget with these two, and I've decided that my calorie budget is 800 calories. My vitamin budget daily level is like 150 mg. So I create a linear program using cp.problem. I supply my objective and constraints. That's it. And then I'll just call linear program.solve. It will give me the results, and I can access the variables from these results. So for example, a.value will give me my number of apples. L.value will give me number of lemons, and the result itself will be the cost, the lowest cost by eating these things, right? And the thing is, if you eat these many things, you will actually satisfy this constraint that you have consumed at least these many calories, which is 800, and these many vitamin C, which is 150 mg. So that's how we write a program in cvxpy. And the thing is, right now, what we are trying to do is what we write in the sheet of paper with hand, right? We write a mathematical formulation, and this library is actually very similar to what we write in the paper. So it's a one-to-one conversion kind of a thing. So actually, this library is very simple to read. That's why we are using it. And what this library does is it helps us to like specify our objective, specify our constraints, and it tries to use multiple solvers in the background. Like these are the solvers like CBC, cvxopt, and there are multiple solvers, right? So basically, in the background, it kind of creates what is needed from these specifications and calls those solvers. And maybe the solvers are expecting inputs in a certain way, but here we have more flexibility in how we define things. It's very readable and it's great for teaching. So so that's like a very simple introduction to a mathematical optimization problem. And I hope this gives you a very good intuition of what is an optimization problem, right? So let's go back to our whiteboard. So we are back to our whiteboard. And I wanted to write the optimization problem in some level of generality. So earlier what we had is we wanted to like minimize over variables apples and lemons. And the cost was like cost of apple times A plus cost of lemon times L. And we had some constraints and we write it like subject to constraints. So minimize the cost subject to certain constraints. And there were 4 constraints, which was vitamin C for A times A plus vitamin C for L times L should be less than vitamin C budget. So let's say we call it vitamin C budget. And then we had calorie constraint. So we can say the calorie of apple times apple. Oh, we should use something else because we have already used C for the cost. So let's say calorie of apple times apple plus calorie of lemon times lemon should is less than equal to our budget, calorie budget. And then we had 2 more constraints on A and L because they should be positive or non-negative, right? So A is greater than equal to 0, L is greater than equal to 0. And I told you multiple times in this itself that these are called constraints. This is called the cost function, or it's also called objective function, right? Now, with this analogy, I want to write this thing in slightly more generality. It's already very general, but I want it to be more general. So what we really want is we want to minimize an objective, let's say f of x over some variable x, subject to some constraints that x belongs to certain set C, right? And soon enough, we will learn the nature of this f and the nature of this C can actually help us solve the problem exactly or approximately depends on the nature. And that's what a lot of what we will immediately cover will entail. So there's something called disciplined convex programming. And what it says is that we want to minimize a function f of x for variable x subject to constraints that x belongs to a set C. And what it assumes is this f of x is something called a convex function. We will see in a lot of detail what is the meaning of convex function, but just for now, just take my word for it that disciplined convex programming should have a convex function as objective and constraint should be a convex set. And these two things are something we will look at immediately, but you can see the kind of some kind of relationship here, right? You can see that this cost is the same as this f of x. So we have this analogy here. And then we have this constraint, right? And this is similar to this x should belong to this convex set. And this is another analogy, right? So basically this class of problem which we just saw is called a linear program. And don't worry about the relationship, what is the meaning of linear program, but when everything is linear, it's called linear program. We'll revisit it. And this linear program is just a special case of convex program, right? So we are just trying to learn something more general where linear program is a special case. There's something called a quadratic program, and there are multiple things. Not all of them are very commonly used, but you'll see that quadratic program and linear program is something which is extremely popular. If you have heard something about a model called support vector machines, a lot of variations of implementation exists, and one of the implementation for support vector machines is in the form of a quadratic program. And we'll see these things, but I just wanted to show you that what we're trying to learn here, which is convex optimization, is like a very general form, but it assumes that certain things are convex, function is convex, objective function is convex, the constraints are convex sets, and so on, right? So that's the main idea. And right now it will feel like it's very mathematical and all, but you'll see how powerful this is. We'll also see a couple of examples where we are solving some real world problems. And even this vitamin C problem is like, for example, a nutritionist might want to use this, maybe, right? So, of course, I mean, for a nutritionist, it will not just be apples and lemons, it will be like everything. And based on the constraints and requirements and everything, and some macronutrients requirement, micronutrients requirements, goals and all, right? So basically, even this problem is like a simplified version of a problem which nutritionist might be interested in, but we'll see a real problem for from like, let's say, advertising or from machine learning. And even before we learn machine learning, we might see how to solve certain optimization problems in abstraction. We don't know that it's coming from machine learning, but somehow we can say that, okay, man, this is an objective function. These are the constraints I want to optimize for the optimal X, right? So the thing is, we will learn this convex optimization space in certain abstraction, and it will feel very dry. It will feel a bit mathematical, but it will make you more mature. Trust me. And it will also accelerate the rate at which you learn in future. It will also build this knowledge map which I keep talking about, right? Like in the first lecture in the live session, I talked about painting the ML canvas throughout your life, right? Or I give you another analogy like object oriented programming, like how classes are structured so that there's no repeated code and how things are organized in some sense, right? Similar to object oriented programming, we can imagine that our knowledge is organized in a certain way, and the tools like linear algebra, probability, optimization, these are abstractions which helps you organize your knowledge in a certain way, and it helps you retain your knowledge for a much longer duration without remembering the specifics, because you are trusting your foundations, and you're trusting that, okay, if I don't remember the specifics, it's fine, because I have my foundations and knowledge arranged in a certain way. I can have a quick recall, or I can create cases from my foundations. So that's the goal. And that's why we are learning convex optimization in machine learning class. And uh, of course, all machine learning problems are not convex, but convex optimization tools and the learnings from it can be applied to non-convex situations as well. The only thing is that convex problems guarantees the solution is the best. The non-convex problem doesn't guarantee that the solution is the best, but it might have some approximate guarantees or no guarantees at all. It depends. So even if we are solving a machine learning problem which is not convex, for example, all neural networks are non-convex, but still we can borrow the tools from optimization, maybe non-convex optimization or global, it's called global optimization, when we can achieve a global optima? I mean, of course, I mean, you don't have to worry about the details, but I'm trying to motivate why we are learning convex optimization. And I just showed you one example so that you can connect with theory. But for next 2 weeks or something, it will feel like whatever you're learning is very dry, but that's okay. Learning doesn't always have to be entertaining. So I'll show you a tweet from Andre Karpathy. Let me do that. Okay. So I just posted this tweet from Andre Karpathy today. So this is the tweet, and it talks about the shortification of learning. So I'll just read it with you. There are a lot of videos on YouTube, TikTok, etc. that give the appearance of education, but if you look closely, they are really just entertainment. This is very convenient for everyone involved. The people watching enjoy thinking they are learning, but actually they are just having fun. People creating this content also enjoy it because fun has a much larger audience, fame, and revenue. But as far as learning goes, this is a trap. This content is an epsilon away from watching Bachelorette. It's like snacking on those garden veggie straws, which feels like you are eating healthy vegetables until you look at the ingredients. Learning is not supposed to be fun. It doesn't have to be actively not fun either. It could be fun as well, but it doesn't have to be necessarily fun. But the primary feeling should be that of the effort. It should look a lot less like that 10-minute full body workout from your local digital media creator, and a lot more like a serious session at the gym. You want the mental equivalent of sweating. It's not that quickie doesn't do anything. It's just that it's wildly suboptimal if you actually care about learning. I find it helpful to explicitly declare your intent upfront as sharp binary variable in your mind. If you are consuming content, you are trying to be entertained, or are you trying to learn? And if you are creating content, are you trying to entertain or are you trying to teach? You'll go down a different path in each case. Attempts to seek the stuff in between actually clamps to zero. So for those who actually want to learn, unless you're trying to learn something narrow and specific, close those tabs with quick blog posts. Close those tabs of learn XYZ in 10 minutes. Consider the opportunity of snacking and seek the meal, which is the textbook, documents, research papers, manuals, long forms. Allocate a 4-hour window. Don't just read, take notes, reread, rephrase, process, manipulate, and learn. And those who are actually trying to create content and trying to educate, please consider writing, recording long form designed for someone to get sweaty, especially in today's era of quantity over quality. Give someone a real workout. That's what I aspire to in my own education work too. My audience will decrease. The one that remains might not even like it, but at least we learn something. And that's a great tweet. And I find it really relevant in terms of trying to aim for excellence. And that's why we are trying to like learn other things which are important for machine learning. I could have compressed this whole course to 3 months. You could have just known all the models in a very superficial way, but I'm spending like almost 1.5 years or slightly less than that to teach you machine learning really well, right? And all this motivation is basically what is telling me that this is a time you should slightly get more informed about optimization.